Today, we will look at some problems about the computation of water surface profiles. For the first problem, example problem 6.9, water depths were recorded at critical diversion points located at distances of 188, 423, 748, and 1675 meters upstream of the dam, and depths were only found at locations 188 and 423 meters upstream. So we need to determine the depth of the flow at the other two diversion points. So the point is 748 and 1675 meters. And using the standard step method and a spreadsheet program. And it has the normal depth being reached in the last cross section. So to solve this problem, we can use an Excel file in the Week9 section on the cross site. This is an Excel file on the cross site. Over here, we can see the information about the channel has been put here. The B, the bottom width of the channel is 4 meters. The Manning's coefficient N equals 0.025. And the size slope x1, the flow rate is 12.5 cubic meters per second. And the slope of the channel equals 0.001. And from the column F to the column R, this is the actual calculation table that we will use. And we will use these equations to determine the parameter values in these columns. I believe that you are familiar with this table since Professor Yang displayed how to calculate step by step in class. And go over here, this orange cell. For this problem, the location that we want to know the water depth is 748 meters away from the dam. So now the delta L should be equal to the 748. And at the section 1, the problem gives us the water depth. Over here is 2 meters. And now we can draw everything down. And one thing we need to fix is the elevation over here, since we define the data at the section 1, so the elevation at the section 1 is 0, and the elevation at the section 2 will be equal to the delta L times the slope. We need to fix the slope, since the channel slope is not changed. And then we will guess the water depth at the section 2. Let me try 1.8 first. So we can see now the total energy had at the downstream is 2.524 meters, and the total energy had at the upstream should equal to the pressure head plus the elevation head plus the velocity head. Since we know the total energy head at the downstream should be equal to the total energy head at the upstream, but now these two values are different, so we still need to guess the water depth at the section 2. After several tries, we can determine that this value should be the 1.735. So now the total energy had at downstream is the same as the total energy had at the upstream. So we can determine that when the delta L equals 748 meters, the water depth should be equal to the 1.735. And then we need to find the water depths at another diversion point. So now the delta L should be equal to the 1,675 meters. And we can see the total energy head at the downstream is different from total energy head at the upstream. So we still need to guess the water depths at the section 2. So after several tries, we can determine that the water depth should be equal to the 1.62045. Now we can see these two values are the same. So now, when the delta L equals 1,675 meters, the water depth is approximately equal to the 1.620 meters. Now we know that when the delta L equals 748 meters, the water depth Y equals 1.735 meters. And when delta L equals 1,675 meters, the Y water depth equals 1.62 meters. And in the example problem 6.9, we know that the normal depth is 1.66 meters, and the water depth that we calculated in the last cross section is 1.62 meters. So we can determine that the normal depth has been reached before the last cross section. So we have done this problem. For the second problem, in example problem 6.9, water depths were required at critical diversion points located at distances of 188, 423, 748, and 1,675 meters upstream of the dam. The standard dam method solution yield depths of 1.91, 1.82, 1.74, and 1.66 meters respectively at these locations. We know that the four values are a little bit different from the four values we calculated from the Excel file. The four depths we got are 1.909, 1.82, 1.735, and 1.62 meters. Professor Yang obtained these two values in class, and we obtained these two values in the previous problem. So we will use the direct step method and a spreadsheet program to solve for the upstream distances using these four depths. And we can still use the Excel file on the cross site to solve this problem. Open the Excel file and switch to the second sheet. This is the direct step method. Over here, the information about the channel have been put here. The concept is almost the same to the previous problem. So we will use these equations to determine the component values in these columns. And we drag everything down since the calculation is the same. The last column here is the column that we need to set up the distance to the dam. And for this cell indicates the distance prescribed in the original example problem. For the first calculation, we know the water depth at the first diversion point is 1.909, and we can see we determine all the component values at this row, and then we need to determine the delta L. So the delta L equals the ED minus EU divided by the slope minus average the slope of energy. So this is a 3 and N4. Now we can see the delta L is the same as the distance prescribed in the original problem. And we can do the same thing to the other locations. The second point located at the distance of the 423 meters upstream of the dam. And we know the water depth at that point is 1.82. You can see the values in these two cells are still the same. Again, the third point located at the 748 meters distance to the dam, and we still know the water depth at that point is 1.735. We can see the two values are still the same. The last point, we know the distance to the dam is 1,675 meters, and we know the water depth at that point is 1.62 meters. And we can see the delta L obtained compare closely to the distance prescribed in the original problem. So after calculating in the Excel file, we can know that the upstream distance obtained compare very closely to the distance prescribed in the original problem. So in other words, we can get a conclusion that the standard step method and the direct step method yield very similar results. So we have done this problem. For the third problem, in this figure, a 10-meter wide rectangular channel carries 16 cubic meter per second flow rate, and it has a roughness coefficient of 0.015 and a slope of 0.0016. Normal and critical depths in this channel yn equals 0.78 meters and yc equals 0.639 meters. If a 5-meter high dam is placed across the channel, raising the water depth to 5.7 meters at a location 5 meters upstream from the dam. And we need to determine the channel and the flow classification and explain your supporting logic. And then we need to determine the water surface profile upstream from the control section by finding the depth of flow distance of 200, 600, 1500, and 3000 meters upstream. From the problem, since we know normal depth is greater than the critical depth, so we can determine the channel is mild. Also, since the depth of flow 5.7 meters is greater than critical, and normal depths. So it is type 1 curve. So we can determine the flow classification is M1 curve. So the depth decreases as we move upstream. So the water depth will decrease as we move upstream. Then we need to determine the water surface profile upstream from the control section by finding the depths of the flow at distances of 200, 650, 100, and 3,000 meters upstream. To solve this problem, we can still use the Excel file on the course site. I believe you are familiar with this Excel file since we have used this table to solve the first problem previously, and now we need to change some channel information to make this table can help us solve this problem. So for this problem, the B, the bottom width of the channel should be equal to the 10 meters, and the N equals 0.015. And since this is a rectangular channel, so the M, the side slope should equal to 0. And the flow rate is 16 cubic meters per second. And the slope of the channel equals 0.0016. We also change the information on this diagram. Q is 16. Slope is 0.016. And we also need to change the diversion point for this problem. The first data L is 200. Second data L equals 600. And the third data L equals 1500. And the last delta L equals 3000. And we also know the Y for this problem. The control section Y equals 5.7 meters. Now we can use this table to solve this problem. So for the first diversion point, delta L equals 200 meters, and we know the in this growing cell, the control section water depth should be equal to 5.7, and we need to guess the water depth in this orange cell. Since we have known that the depth decreases as we move upstream, so the value should be less than the 5.7. So after doing several tries, we can determine that the water depth at the first diversion section is 5.38. So now we can see the total, these two red cells. The total energy had at the downstream is the same as the total energy had at the upstream. So we can determine at the first diversion point, when the delta L equals the 200, the water depth should be equal to the 5.38. So when delta L equals 200 meters, the water depth is 5.38. And for the second diversion point, delta L equals 600. And again, after doing several tries, we can get the water depth is 4.742. We can see these two values are the same. So when the delta L equals 600, water depth is 4.742. For the third diversion point, delta L equals 1500. And again, you can determine the water depth is 3.311. And for the last diversion point, delta L equals 3,000 meters. So we can determine the water depth is 1.312. 1.312. So after using the Excel file, we can determine when delta L equals 200, the water depth Y equals 5.38 meters. So when delta L equals 600 meters, the Y water depth equals 4.742 meters. When delta L equals 1500 meters, water depth equals 3.311 meters. When delta L equals 3000 meters, water depth equals 1.312 meters. So we have done this problem. For the first problem, we need to determine the flow rate in 6.5 feet times 6.5 feet concrete, the culvert, if the headwater is limited to a depth of 30.3 feet above the invert, and the culvert has a square-edged entrance and is 50 feet long, with a slope of 1.0%. Assume that the outlet is not submerged. So for example, the hydraulic operation, category C. But once the flow rate is found, we need to verify that it is not a category B by checking the normal depth. So the first, we're assuming hydraulic flow classification C. So in this case, we know the Q equals the CD times A times square root of 2G times H. And the CD is the coefficient of discharge, and from the page 333 in the textbook, we can know that the common value used in practice is CD equals 0.6 for square-edged entries. So for this problem, we know the CD should be equal to the 0.6, and then we know the A equals 6 feet squared, and H is the depth above the culvert center, so the H should be equal to the headwater elevation YU minus D over the 2, since we know the YU in this problem equals 13.3 feet and the D equals 6.5 feet. So we can determine the H equals 13.3 feet minus 6.5 feet over 2. So now we can determine that the Q should be equal to the 645 cubic feet per second. So now the flow rate is found, And we need to verify that it is not category B by checking the normal depths. So to check the normal depths, we will use figure 6.4 in the textbook. And this is the figure 6.4a in the textbook. We know the x-axis is the value of this equation, and from this problem we know the n should be equal to the 0.013, since we know this is a concrete culvert. And the Q we calculated before is 645 cubic feet per second, and Km should be equal to the 1.49, since the unit in this problem is British system, and S0 equals 0.001, and a B equals 6.5 feet. So now we can determine the value of this equation, and Q over the Km times S01 to the power of 1/2 times B to the power of 8/3 equals 0.38. So we're wrong in, and at this location the value is approx equal to the 0.38, and we draw the vertical line from this point to intersect with this rectangular curve. So we can find that the yn over the b is equal to the 0.8, and we know the b equals 6.5 feet for this problem, so we can determine that the yn, the normal depth, equals 5.2 feet for this problem. So since the yn is less than 6.5 feet, so we can determine this is a flow classification C, and the Q equals 645 cubic feet per second. So we have done this problem. For this problem, the city engineer is concerned about damage to homes upstream of a box culvert during the 100-year flood event. And we know the flow rate equals 12.5 cubic meters per second, and a 2 meter times 2 meter concrete culvert with a square-edged entries condition is 50 meters long, and it has a bottom slope of 2.0%. Backward computations show that the tile water depth is 2.75 meters above the invert of the box culvert during this flood event. And upstream water depth of 3 meters will begin to flood homes. Other homes in danger of flooding, and we also need to determine the velocity of flow through the culvert. So from the problem, since the outlet is submerged, so the flow classification is A. So in this case, we know the head loss equals the entrance loss plus the friction loss plus exit loss. And this equation also equals the Ke times V squared over the 2G plus n squared times v squared times L over the RH, hydraulic radius to the power of 4 over 3 plus v squared over the 2g. This is equation 8.17b in a textbook. And for a squared edged entries, we know the KE should be equal to the 0.5. And we know the RH, hydraulic radius, equals A over P. From the problem, we know the A equals 4 square meter, and for covered flowing full, the P, the weight, the parameter, equals 8 meters for this problem. So we can determine the RH equals 0.5 meter. And this is a concrete covered, so we know the N, the Manning's coefficient, equals 0.013, and we know the L, the length of the cover equals 15 meters, and we also can determine the velocity equals Q over the A, so it should be equal to 12.5 cubic meters per second over the 4 square meters, so velocity equals 3.125 meters per second. This is velocity. So now we can determine the head loss. So the head loss should be equal to 0.81 meters. And then we will balance the energy between the entries and exit and assume the datum at the exit, so we can get the equation. So YU plus S0 times L equals YD, the water depth at the downstream, plus the head loss. Since we know the S0 equals 0.02 and the length equals 50 meters, and YD, we know the YD equals 2.75 meters. Oh, sorry. YD 2.75 meters. And we know HL equals 0.81 meters. So we can determine the YU equals 3.26 meters. And since we know YU is greater than 3 meters, so we can determine that the home are in danger during the 100-year flood. So we have done this problem. For the last problem, we need to determine the size of circular corrugated mantle culvert that will fulfill these design conditions. 200 feet length, the slope is 0.1, and the flow of 88.2 cubic feet per second. The outlet will be unsubmerged, but the inlet, square-edged, will be submerged with a head water depth of 6.6 feet above the culvert invert. So since the outlets will be unsubmerged and inlets will be submerged, so the culvert must be flow classification B or C. So for flow classification B, we balance the energy between inlet and outlet and assume the data at outlet. So the equation is y sub u, the head water depth plus S0 times L equal the D plus the head loss. This is the diameter of the pipe. So from the problem we know the slope equals 0.1 and the length equals 200 feet, and the head water depth y sub u equals 6.6 feet. So we can determine the head loss equals 26.6 feet minus d. This is equation 1. And according to the equation 8.18 in the textbook in the British unit, we know the head loss also equals Ke plus n squared times L over the 2.22 times RH to the power 4 over 3 plus times 2g plus 1 and times 8 times q squared over the pi squared times g times d to the power 4. This is equation 8.18 in the textbook in the British unit system. And we know this is a square edge entries, so we know the Ke equals 0.5, and we know this is a corrugated mantle. So from the table 6.2, we know the coefficient of Manning's coefficient n equals 0.024. This is from the table 6.2 in the textbook, and we know the L equals 200 feet. And the RH, hydraulic radius, equals D over the 4 for pipe flowing full. And we know the Q equals 88.2 cubic feet per second. So now we can determine that the HL equals 0.5 plus 0.024 square times 200 over the 2.22 times d over the 4 to the power of 4 over 3 times 2g plus 1 times 8 times 88.2 square over the pi square times g times d to the power 4. This is equation 2, and equating equation 1 and equation 2 is 26.6 minus d equals 1.5 plus 21.2 over the d to the power 4 over 3 times 196 over the d to the power 4. So we can determine the d equals 2.75 feet. So this is for the diameter of this pipe is for the classification B. And for classification C, and we know the Q should be equal to the C sub D times A times square root of 2G times H. And we know for square edged entries, the CD should be equal to the 0.6, and we know the A equals pi times d square over the 4, and the H is the depth above the cover center, so H should be equal to 6.6 feet minus D over 2. And we know the Q equals 88.2 cubic feet per second. So now we can determine that the D, the diameter of the pipe, equals 3.25 feet. And often, the larger diameter is selected in practice, so the culvert will operate under flow classification C, and the required D should be equal to 3.25 feet. So we have done this problem.